Everything we've done so far we could have done with point masses. You didn't need to know how many centimeters across the rock was that you threw in the air or the block sliding down an inclined plane. None of that has been important. Sometimes the mass has been important, but that's it. For real objects, they're extended bodies, they're not point masses. And the first thing that we're going to look at about that is their center of mass. If we have a uniform object, so it's the same density everywhere, like a bottle full of water, the center of mass and the geometric center are at the same place. So if we have a sphere, the center of mass is at the center of the sphere. Same for a cube or a cylinder or anything like that. We'll have to do some more math if the shape is more complicated, and we have to keep in mind that there may not be any mass at the actual center of mass. For example, think about a donut. Center would be in the center of the hole where there's nothing there. If we have a collection of point masses, the way we would find this is we multiply each mass by its position, x, y, or z, whatever we're talking about, coordinate, and then sum the products, and then we divide by the total mass so that we get something with dimensions of position again. We could write that like this, and this is actually where the term weighted average comes from, which is the idea that getting 100 on a quiz is not the same as getting 100 on the final exam. If we want to calculate one of these, in the picture below, let's say the green point has a mass of 7 kilograms and the red point has a mass of 1.5 kilograms. Green is 0.2 meters away from our origin, red is 0.9. So our center of mass says multiply each mass by its position, add them together, and then divide by the total mass. And here we get 0.323 meters. Does the origin of our coordinate system matter? It does in terms of the number, but not in terms of the absolute position. If we measured from the other end of the meter stick, we'd say the red dot is at negative 0.1 meters, and the green is at negative 0.8 meters. We then plug that into the same formula, and now we get negative 0.6765, but notice this is the same position as 0.3235 from the right. If we have, instead of a bunch of point masses, if we have a continuous object, we use integrals instead of sums. So we would do the integral of x position, every little tiny piece of mass, what is its x coordinate, integrate all those things and divide by the total mass. And of course we could change x to y or z to find the center mass along those axes. If we want to do this physically for a weird shaped object, we could do something like hang it from a string. The center of mass will always be below the point of attachment of the string. So if we take this mess and we have this string here and then we hang it from that string, it'll hang straight down, and we notice somewhere along this line is the center of mass. So we could draw a line with a pencil there. Then we pick a different point to suspend it from, let's say here. When we do that, now the center of mass is along this line. The point where the two cross, that must be the center of mass. We could also balance the object on a point like a nail or a fingertip, and if the center of mass is above that point, you can balance it. Next, we're going to use this to make a small change to Newton's second law, because what it really talks about is the acceleration of the center of mass. So instead of just A, we should be saying A center mass. The way you can imagine this being important is if you take something like a baton or a hammer and throw it in the air, you know it would probably tumble end over end as it flew. And if you put a marker on the bottom of the handle, you'd see it making this complicated pattern of loops as it flew through the air. However, if you just put a dot on the center of mass of the hammer, you'd see it makes the same arc, the same parabola, the same path that all of our point masses, our rocks, used when we were looking at projectile motion. The rest of the hammer spins around that, but the center of mass itself just moves in a simple way. We can now use this idea to define linear momentum. This is mass multiplied by velocity, so it's a vector. The units are just kilogram meters per second, and there's apparently no unit attached to that with a shorter name. And you could ask, why do we have to have momentum at this point? We already have a quantity that describes mass and velocity, but kinetic energy. Why do we need another one? Why can we not just have an infinite collection of these with all sorts of weird numbers, whatever weird measurement we want to make, we multiply by it or divide by it or whatever. The reason is you can do this, but nobody's going to care about the number that you get for this mass times height divided by shoe size times blood pressure, because it's not conserved. It changes as you get older, heavier, taller, change shoe sizes, and during the day as your blood pressure goes up and down. So there's not really any value to this as far as we know. The reason we care about energy is that it's conserved. That's the same reason we care about momentum. There are circumstances where it's conserved so we can solve problems with it. If we want to figure out what those circumstances are, we do the final modification of Newton's second law. And that is, we see that it should really say some of the external forces is dp dt of the momentum. Now again, this is momentum of the center of mass, but it gets tiresome to write that over and over, so we're just going to drop it and assume you realize it's there. We can write that using the basic calculus. We get m dv dt plus v dm dt. For everything we've done so far, the mass hasn't changed with time, so this term would be 0, and we end up with m dv dt, which is of course just ma. This is the reason we start you out small with F equals ma. What it should really be is F equals dp dt. If momentum is conserved, that means pi equals pf at different times. That would mean dp dt is 0. So, using this, the way dp dt gets to be 0 is if all the external forces sum to 0. So, for example, if we have a 1 kilogram rock and we drop at 1.25 meters, before we let go of it, momentum of the rock is 0, but just before impact it'll be going about 5 meters per second, so PF is negative 5 kilogram meters per second in the j-hat direction. This is obviously not conserving momentum. Pi and PF are not the same, and it's because of the external force of gravity. We could say, alright, let's expand our system to include the Earth. If we do that, gravity is an internal force now and it won't count. We get the same answers for the rock, but how do we make this work? It turns out that what will happen is the Earth's momentum starts out to be 0, and as you let go of it just before it collides with the rock, the Earth will have this upward momentum, which is tiny. The total momentum is the sum of these things, so we have 0 from the rock plus the Earth before, and 0 from the rock plus the Earth just before impact. This may seem like you're cheating a little bit, and just because it's impossible to prove that the Earth moves with this ridiculously small speed, because when we divide this 5 kilogram meters per second by the Earth's mass, we'll get something about 10 to the negative 24 meters per second. So think about what would happen if you were in space with two 1 kilogram rocks. They would be attracted to each other gravitationally, and we'll see more about that in a later chapter, and they'd move towards each other and they would meet in the middle. They'd have to meet in the middle because there's no other way by symmetry. There's no other place they could meet. You can't say closer to the heavier one because they both have the same mass. What about 1 kilogram and 10 kilogram? Here we're going to see the big rock moves, but not as much as the little rock. They're going to move in inverse proportion to their masses. We can just keep making this 10 kilogram rock larger and larger, and eventually we've got the Earth. The most common thing we use conservation of momentum for is collision problems. So let's say we have an 1800 kilogram car moving 20 meters per second north, and it hits another truck at an intersection moving 10 meters per second east with a mass of 6,000 kilograms. They collide and stick together, so what happens to the wreckage? And the first thought here is we can't use conservation of momentum because we've got external forces like gravity, normal force, and friction that are involved. We don't have any velocity in the vertical direction anyway, so the vertical direction forces don't make any difference. Gravity and normal force are not important. Friction, however, does act in a direction opposed to the velocity. The friction is going to ruin conservation of momentum for us because the wreckage doesn't keep moving forever. It does slide to a stop. However, what if instead of forever in the future and forever before the collision, we looked at a millisecond before and after the collision? How much of an impact does friction have then? The acceleration on flat ground will be negative mu kg. This is what we got from the chapter on forces. But the change in velocity in 1 millisecond will be that acceleration times t, which is very, very small. If that seems like too large of a velocity change for you, look 1 microsecond before and after the collision. The idea is if we make that time window small enough, we can always say initial and final momenta are equal. So now we go back to the collision. We have our initial x momentum from the truck, 6,000 times 10 meters per second. Initial y momentum from the car, 1,800 kilograms times 20 meters per second. At the end, we have one combined lump, 7,800 kilograms, moving with some velocity in the x direction, and the same lump moving with some velocity in the y direction. This conservation of momentum is really two formulas, so it's Pfx equals Pix right here, and we get that the final x velocity must be 7.69 meters per second. We apply the same thing to y, we get that Vy final is 4.62 meters per second. Now we can make a final velocity vector, just like we did in the vector chapter, of about 9 meters per second. And the direction, they're going 30 degrees north of east. Now you could figure out how far they slide until they stop this is just a kinematics problem at this point because you have a velocity, and if you have your acceleration of negative mu kg, if they're on flat ground, it's just a kinematics problem to find the distance